As we speak, the world's attention is held captive by the Japan Trench. Every seismologist, every news algorithm, and every headline is locked onto the aftershocks of the M7.5 event and the active megaquake advisory. It is the visible story, the anchor for our global anxiety. But while the collective gaze is fixed on the Pacific, something quiet, something structurally strange is happening elsewhere. Two of the most heavily instrumented volcanic systems on Earth, separated by 9,000 miles, have simultaneously entered a state of boundary condition instability. In Hawaii, a volcanic system that had operated with the precision of a mechanical clock for 44 consecutive cycles has just broken its script. And in Italy, a caldera sitting beneath 6 million people just produced a seismic pulse that triggered school evacuations. On the 9th of April 2026, the U.S. Geological Survey published 3 words that should stop you cold. The cause is uncertain. This is not an admission of ignorance or a failure of technology. It is a signal that our most sophisticated models have reached their edge. We have more data than at any point in human history. Yet for the first time in 44 cycles, the Earth is doing something the instruments can see perfectly clearly, but cannot explain. We are entering an observation window where the map of our experience has reached its margin, and the territory beyond is genuinely uncertain. Today, we go inside the anatomy of chaos to investigate why the data is finally moving faster than our ability to understand it. To understand why the current events at Kīlauea are so unsettling to the scientific community, one must first appreciate the extraordinary regularity that preceded them. For months, Kīlauea had been operating with a degree of behavioral consistency that is almost unheard of in natural, high-energy systems. Since January, the volcano had followed a near-perfect mechanical script. Magma pressure would build, the ground would swell, a threshold was crossed, and lava would break to the surface. This cycle of inflate, erupt, deflate, repeat occurred 44 times with a regularity that earned it the nickname of a geological heartbeat, the truncated peak of episode 44. On April 9, 2026, that heartbeat skipped a beat. Episode 44 terminated at 7:41 p.m. HST after only 8.5 hours of activity. In the 43 previous cycles, the volcano consistently reached a specific inflation peak, a mechanical tipping point where internal pressure finally overcame the structural resistance of the rock. However, episode 44 ended prematurely, without ever reaching that expected threshold. For the volcanologists at the Hawaiian Volcano Observatory, HVO, this wasn't just a shorter eruption, it was a structural red flag. If the system failed to complete its normal pressure release, a critical question emerged. Where did that unreleased energy go? The South Rim Anomaly. The answer began to appear almost immediately, but not where anyone expected. During the transition window into what should have been episode 45, the monitoring network detected a cluster of 15 shallow earthquakes. These weren't occurring beneath the main summit vents or the established magma reservoir. Instead, they were displaced roughly 1 mile beneath the south rim of the Halemaumau crater, a region that, in normal cycle behavior, is not supposed to generate its own independent seismic signal. Simultaneous with these quakes, ground deformation instruments recorded something even more startling: localized uplift in that same south rim region. This wasn't measured in microradians, the tiny angular units typically used to describe volcanic tilt, but in inches of actual vertical displacement. The Earth was physically rising in a location that sat entirely outside the established pressure center of the magma system, a model in crisis. This combination, shallow seismicity and localized uplift outside the known geometry, does not map onto the Kīlauea playbook. In volcanology, the data is spatially incoherent, meaning the signals are appearing outside the expected mechanical envelope of the system. This led the U.S. Geological Survey to issue that haunting 3-word sentence: the cause is uncertain. In the world of institutional science, those words are an alarm. They signify that the instruments are functioning perfectly and the data is clean, but the physics generating that data has moved beyond our current theoretical framework. The model that successfully forecast 44 consecutive episodes is, for the first time, no longer adequate to describe reality. How could a system so predictable suddenly reconfigure its entire plumbing network? To find the answer, we must look at the competing theories currently under debate at the HVO. The uncertainty at Kīlauea's south rim has forced volcanologists into a high-stakes process of elimination. Three primary frameworks are currently competing to explain why the ground is rising in the wrong place. The first is lateral magmatic intrusion. In this scenario, magma that should have fueled a full episode 44 diverted sideways into the shallow rock of the south rim. This explains the 15 anomalous earthquakes and the localized uplift. However, this theory faces a staggering physical contradiction. From April 9 onward, instruments recorded a cumulative summit uplift of approximately 16.5 microradians. In a simple, single reservoir system, diverting magma to a side branch should draw pressure away from the summit, causing deflation. Instead, both the summit and the south rim are inflating simultaneously. This leads to a more complex possibility. Kīlauea may be operating as a multi-reservoir system. If the south rim has its own independent pressure zone, a secondary pocket activated during the episode 44 transition, then our 4-4 cycle model isn't just hootnip skipping a beat, it is fundamentally incomplete. Alternatively, the hydrothermal overpressure model suggests the south rim signal isn't magma at all, but superheated water and steam fracturing the shallow crust. This would explain why the south rim can inflate without drawing from the summit's magma budget. Across the 9,000-mile gap, the Campi Flegrei pulses, the 7-2-hour observation window at Kīlauea, began to close a window where the system's initial character starts to reveal its long-term direction. Another boundary condition. Instability flared up 9,000 miles away in Italy. Unlike the remote reaches of Hawaii, Campi Flegrei is a caldera system embedded in the urban fabric of Naples. Here, the human stakes are measured in the 6 million people exposed to its potential hazards. On the 8th of April, 2026, the ground beneath Naples produced a seismic pulse that the scientific community could not ignore. A seismic swarm, peaking at a magnitude of meta 3.3 to 3.4, struck the Pozzuoli Academia region. These were shallow events, but they were accompanied by significant gas and heat anomalies. The response was immediate. School evacuations were triggered as a precaution, a sobering reminder that for the residents of the burning fields, geological unrest is a persistent texture of daily life. The invisible risk, hydrothermal failure. While the media often gravitates toward the cinematic myth of a super eruption, the actual danger at Campi Flegrei is far more subtle and immediate. The real risk, highlighted by the April 8th swarm, is hydrothermal failure, also known as a phreatic explosion. Beneath the caldera lies a pressurized network of geothermal reservoirs. When the mechanical integrity of the overlying rock, already weakened by centuries of acidic volcanic gases, finally gives way, the result is a catastrophic release of steam and debris. The warning time for such an event is measured in minutes, not days. At the center of the caldera, ground uplift has been accelerating, with current rates reaching approximately 10 plus or minus 3 millimeters month since early 2026. Since January 2025, the Wright Station has documented a total vertical displacement of nearly 26 centimeters. At both Kīlauea and Campi Flegrei, we are seeing the same meta-problem. We have more data than any generation in history, but we are entering territory where that data exceeds the explanatory capacity of our models. The Earth is running multiple large volcanic systems at their operational edges simultaneously, and the next chapter of our understanding is being written in the ambiguities of the data. When highly anomalous events occur simultaneously on opposite sides of the planet, the human brain performs one of its most evolutionary functions. It connects them. We are wired for pattern recognition under uncertainty. If Kīlauea's south rim deviates from a 4-4 cycle pattern just as Campi Flegrei produces a gas-venting seismic swarm that evacuates schools, our default assumption is that they are linked. The mind immediately conjures images of a deep mantle pulse, a sudden tectonic reorganization, or a synchronized global awakening. Let me be precise. The science does not support this temptation. The distance between Hawaii and Naples is 9,000 miles. Under current solid Earth mechanics, the stress transfer required to simultaneously activate independent magmatic systems across that distance is physically inadequate. What is happening beneath Halemaumau is not causing the ground to swell beneath Pozzuoli. But if they are not physically connected, how do we explain the simultaneity? In science, there are two kinds of coincidence: pure statistical accident and independent responses to a shared background condition. Think of multiple trees in a forest showing stress responses at the exact same time. They are not communicating, nor are they causing each other's distress. They are responding independently to the same drought. Right now, multiple large-scale systems are operating at the edges of their modeled envelopes. They are not linked by a catastrophic trigger, but they share a profound condition. They are simultaneously generating data that our predictive frameworks cannot resolve. If this boundary condition instability is so significant, why isn't it dominating the news? The answer lies in the structural vulnerability of our attention. The M7.5 earthquake in the Japan Trench created a massive attention gravity well. The megaquake advisory was appropriately calibrated, but it created a media framing in which Japan was the only active story. Everything else became background noise. The attention economy is a finite resource. When public anxiety and algorithmic tracking are saturated by a highly visible disaster, other critical signals are masked. The Kīlauea swarm was logged. The Campi Flegrei uplift was documented. But the translation of that pristine monitoring data into public awareness was delayed because the world was simply looking the other way. While the world watched Japan, other colossal systems were quietly adding data points to this picture of planetary restlessness. In the Pacific Northwest, the Cascadia subduction zone began showing elevated, slow slip tremor activity, gradual, creeping releases of tectonic strain rather than violent ruptures. Simultaneously, Mauna Loa registered a mild increase in shallow seismicity. Neither event suggests imminent disaster, but placed against the backdrop of Kīlauea and Campi Flegrei, they outline a planet currently operating above its quiet baseline. Yet, the most informative data point we have is a negative one. Yellowstone remains completely silent. Its seismicity and gas emissions are perfectly normal. This silence is crucial because it acts as the ultimate scientific veto against the global apocalypse theory. If a massive, planet-wide trigger were activating the Earth's calderas, Yellowstone, one of the most sensitive systems on the globe, would absolutely respond. It is not responding. And that brings the mystery back inward. We are not facing a coordinated global uprising. We are facing something more subtle and scientifically daunting: the realization that our predictive models are currently smaller than the Earth itself. If Yellowstone is quiet, we must confront a scientifically daunting reality: the meta-problem. Humanity is living in an era of unprecedented geological observation. Our monitoring networks are marvels of engineering, featuring seismometers that pinpoint tremors to within meters and GPS arrays, measuring millimeters of crustal deformation from space. The data collected right now is richer and more precise than at any moment in human history. And yet, across multiple heavily instrumented calderas, this pristine data is generating signals that our best predictive models cannot cleanly explain. This is not a failure of science. When the USGS or Italy's INGV publish bulletins stating that the mechanisms behind their data are ambiguous, they are exercising the highest form of scientific integrity. They refuse to force new, complex realities into old, comfortable boxes. They are publicly acknowledging that we have reached the boundary of the map, the absolute edge of the territory that historical experience can accurately describe. We are not seeing more anomalous activity because the Earth is suddenly tearing itself apart. We are seeing more because, for the first time, we actually have the eyes to see it. A century ago, the Kīlauea South Rim anomaly would have been invisible. Today, we track every microscopic twitch, learning that the Earth is vastly more complex and nonlinear than previous, coarser observations ever suggested. The data is moving faster than our models can evolve. How do we process a world where the most sophisticated warning systems on Earth are telling us we are watching, but we are not entirely sure what we are seeing? The answer lies in resisting two dangerous human impulses: panic and complacency. Applying a short-term sense of doom to Kīlauea, a system accumulating pressure over decades, is an error leading to chronic anxiety. Conversely, applying a patient mindset to Kīlauea, a system capable of radically reconfiguring its internal plumbing in days, is a profound failure of situational awareness. Both hazards are immensely real and require serious attention assessed through their unique timeframes. While the global media's attention gravity well remains anchored to the Japan Trench, the deeper story is being written in the quiet ambiguities of these calderas. Kīlauea is demonstrating that a system which operated with perfect regularity for 44 cycles can break its pattern on cycle 45 without proportional changes in its environment. Kīlauea is proving that a heavily populated caldera can maintain a state of persistent unrest that continually tests the nerves of millions without offering a clean answer. The Earth is not building toward a synchronized apocalypse, but it is undeniably slipping out of the predictable rhythms we had grown so comfortable relying on. As we continue to monitor the data, we must embrace the humility of this moment. Ultimately, the most terrifying thing isn't the sight of an eruption finally breaking the surface. The most genuinely unsettling moment is the quiet pause before it, the exact moment when the world's top scientific institutions look at their screens, analyze the highest fidelity data ever recorded, and publicly admit that they are still trying to understand exactly what is happening beneath our feet. The system is speaking. Our only job is to listen. When a volcanic system moves into the unknown, scientists rely on a critical period known as the resolution window. For Kīlauea, this is the 7-2-hour decision window following an anomalous signal. This time frame is not arbitrary. It represents the duration required for an evolving anomaly to distinguish itself from competing explanations. During these 72 hours, the system starts telling you which story it is actually writing. Within this narrow window, 3 distinct scenarios bracket the range of possibilities. The first scenario is dissipation. Under this trajectory, the South Rim anomaly simply fades away. The seismicity rate declines over days, the ground uplift stabilizes, and the signal drops below the noise floor. This outcome suggests a transient hydrothermal pulse or a small magmatic intrusion that stalled and was absorbed into the rock without further surface expression. If this unfolds, the explanatory authority of the Kīlauea model is largely restored. The second scenario is stabilization. Here, the anomaly neither grows nor dissipates. It persists at an elevated level, establishing a new background condition. The seismicity continues at a moderate rate, and ground deformation holds at a new, higher level. This means the system has established a brand new pressure compartment, a secondary node in the magmatic or hydrothermal plumbing that was never active before. The model wouldn't break, but it would fundamentally expand, requiring scientists to track a second variable moving forward. The third scenario is escalation. The anomaly actively grows. The seismic cluster migrates directionally, indicating an advancing fluid front slicing through the subsurface rock. Ground deformation continues to build rather than plateauing, proving ongoing pressure input from depth has not reached equilibrium. This trajectory points heavily toward an active lateral migration event, forcing an escalating monitoring response and reshaping our understanding of where pressure might breach the surface. But volcanoes do not politely pause one process while we figure out another. While the HVO watches the South Rim, the summit system continues to inflate independently, building toward what should be episode 45. The team is simultaneously monitoring 2 parallel pressure systems in a configuration that has never presented itself at the exact same time. For Kīlauea, the equivalent resolution window operates on a scale that makes Kīlauea's 72 hours look like a sprint. The Italian caldera does not answer questions in 3 days. Its timeline plays out over weeks, months, and years. Scientists watch the rate of ground deformation, not just absolute uplift, but whether the rate of change is increasing or holding steady. They monitor gas chemistry, looking for a shift toward high-temperature magmatic gases like sulfur dioxide, which would indicate that the source of the unrest is moving upward. Both observation windows are open right now. The short clock in Hawaii counts down in hours, while the long clock in Italy measures time in months. The data pouring into these windows will either close the hypothesis space and restore confidence, or shatter the models entirely, revealing complexities we never anticipated. Patience is not passivity here. It is the absolute requirement of honest science. The Earth writes its next chapter in the only language it has ever spoken: pure data. As we wait for these observation windows to close, we are left to confront a reality that is far more unsettling than any cinematic disaster narrative. But we must also recognize a profound, almost paradoxical truth about the anxiety we are feeling right now. The discomfort we experience when we look at the anomalous data from Kīlauea's south rim or the escalating uplift beneath Campi Flegrei does not stem from a sudden, violent shift in the Earth's temperament. It stems from the fact that, for the very first time in the history of our species, we finally have the eyes to see it. A century ago, the Kīlauea South Rim anomaly would have been completely invisible. The seismometer network required to capture a cluster of 15 micro-earthquakes a mile underground simply did not exist. The GPS arrays measuring inches of localized uplift from orbit were the stuff of science fiction. If this exact deviation had occurred in 1926 instead of 2026, it would have passed entirely unrecorded. It might have resolved quietly into the rock, or it might have triggered a new vent, but the scientific community would not have seen the precursor. They would have only seen the aftermath. We are the first generation of humans with the instrumentation necessary to watch volcanic and tectonic systems at this level of spatial and temporal resolution in real time. And what we are discovering, as our data streams accumulate and our sensors grow more sensitive, is something that must fundamentally recalibrate how we think about planetary activity. The Earth is considerably more active, significantly more complex, and vastly more capable of operating near its behavioral thresholds than the coarse, limited instrumentation of previous centuries ever led us to believe. We are not seeing more anomalies because the planet is tearing itself apart. We are seeing more because our vision has finally cleared. This brings us to the most crucial distinction viewers must understand: the core philosophy of investigative meteorology. The models we built over the last several decades, the frameworks that allowed us to comfortably predict 44 cycles of Kīlauean eruptions, were built on a singular, foundational assumption: that the systems would, in their essential behavior, resemble what we had already observed. We assumed the past was an adequate, comprehensive guide to the present. When systems start doing unfamiliar things, those assumptions do not shatter, but they begin to show their edges. The models are not wrong. They are simply reaching the boundaries of the territory they were designed to describe. We are standing at a genuinely fascinating moment in human history. The monitoring infrastructure we have built is generating data faster than the interpretive frameworks built alongside it can fully process. Multiple independent systems are simultaneously generating signals that their respective models cannot resolve into clean explanations. The honest answer to what is causing this is, currently, we are not certain. And that honest uncertainty, coming from the most prestigious scientific institutions on the planet, is a signal of discovery. It is the Earth reminding us that it is still vastly larger, more layered, and more deeply complex than our mathematical approximations of it. As we monitor these systems, we are not doing it alone. We are watching this unfold as a global community. So, I want to ask you, where are you watching from right now? Drop your location in the comments. Let us build a real-time map of the people who are paying attention while the rest of the world looks the other way. Whatever happens in the next 72 hours at Kīlauea, and in the next weeks and months at Campi Flegrei, the instruments will keep running, the scientists will keep watching, and the data will continue to flow. Somewhere in that gap between what the instruments can measure and what the models can currently explain, the next chapter of our understanding of this planet is being written in real time. Sometimes, the most terrifying thing isn't an eruption that has already begun. The most deeply unsettling moment is the quiet pause before it, the exact moment when science must publicly admit that it is still trying to understand exactly what is happening beneath our feet. Stay vigilant, stay prepared, and never look away. As we observe geological systems reaching the edges of their predictive models, a much more uncomfortable reality begins to surface. The models currently failing to anticipate the behavior of Kīlauea and Campi Flegrei are not the only systems calibrated on a past that no longer exists. Our entire modern infrastructure, the intricate, interwoven overlay of power grids, supply chains, communication networks, and civil defense protocols, is built upon the exact same foundational assumption that the Earth will remain as stable and predictable as it was during the 20th century. When we talk about boundary condition instability, we are not just talking about magma reservoirs and hydrothermal pockets. We are talking about the structural integrity of the modern world. Consider the reality of Campi Flegrei. The hazard is not just a localized phreatic explosion. The true hazard is the cascading failure of the human systems layered on top of it. A sudden hydrothermal rupture beneath the urban density of Naples would not just destroy physical structures. It would instantly sever power grids, rupture municipal water lines, and paralyze transportation corridors. The evacuation protocols currently in place, designed around the assumption of a multi-day warning window for a magmatic eruption, would be rendered entirely obsolete by an event offering only minutes of precursor activity. This is the invisible disaster. The true danger of a non-linear Earth is not just the sheer physical force of nature, but the devastating realization that our human overlay is fundamentally brittle. We have optimized our grids for the normal operating regime of a planet that is actively demonstrating it no longer wishes to remain in that regime. But we must push the analysis one step further, into the realm that emergency planners refer to as the nightmare scenario. We do not live in a vacuum where geological anomalies politely take turns with atmospheric or astronomical events. We are entering the era of the compounding anomaly. Imagine a scenario where the 72-hour resolution window at Kīlauea escalates into a major lateral intrusion, forcing widespread evacuations. Now, imagine that exact observation window coinciding with an unprecedented, out-of-season atmospheric river, a massive conveyor belt of tropical moisture making landfall on the exact same geography. We are no longer dealing with a singular volcanic hazard. Heavy, relentless rainfall destabilizes the ground that is already inflating from magmatic pressure, triggering massive landslides, wiping out evacuation routes, and blinding the GPS deformation arrays that scientists rely on. Simultaneously, imagine a severe geomagnetic storm, an X-class solar flare, hitting the Earth's weakening magnetic shield. The power grid drops, the communication networks fail. The monitoring instruments, the very eyes we rely on to read the Earth's signals, go dark. This is not Hollywood fiction. This is statistical inevitability in a non-linear system. When multiple independent planetary systems, geological, atmospheric, and solar, simultaneously operate near their threshold boundaries, the probability of them overlapping ceases to be zero. Our predictive models treat disasters as isolated variables. They calculate the risk of an earthquake or the risk of a flood. They do not calculate the catastrophic synergy of an earthquake, fracturing a weakened dam during an unprecedented deluge, while a solar storm takes out the early warning sirens. This brings us to the ultimate question. If the institutional models are struggling to keep pace with the Earth's changing behavior, what is our responsibility as individuals? We must stop outsourcing our situational awareness. The era of waiting for a news anchor to tell us whether we are in danger is over. The investigative meteorology approach is not just a method for analyzing data, it is a required mindset for survival in the 21st century. We must learn to read the data ourselves. When you see an anomaly, whether it is a cluster of shallow earthquakes sitting just outside a caldera's established geometry, an unusual atmospheric pressure drop, or a spike in geomagnetic activity, do not dismiss it as statistical noise. Pay attention. Cross-reference it. Watch the data windows. The Earth is broadcasting its intentions in real time, written in the language of pure physics. The map of our past experience has run out, and we are sailing into uncharted territory. Our civilization's infrastructure may be brittle, but our minds do not have to be. Prepare your households, stabilize your immediate supply chains, but most importantly, keep your eyes on the data. The models may be blind, but we do not have to be. Stay vigilant, stay objective, and never look away. As we stand on the precipice of this new observational era, we must confront a profound philosophical shift. For the past century, humanity's relationship with the Earth has been defined by an architecture of hubris. We believed that if we could just build enough sensors and write elegant enough algorithms, we could tame the chaotic variables of our planet. We treated the Earth as a complicated machine that could be reverse engineered. But Kīlauea and Campi are reminding us that the Earth is not a machine. It is a living, non-linear entity. When Kīlauea's episode 44 failed to reach its inflation peak, and the south rim swelled with displaced pressure, the planet explicitly rejected our mechanical assumptions. When Campi forced school evacuations over a localized M3/4 seismic pulse, the caldera demonstrated that our human timelines mean absolutely nothing to a system that measures time in millennia. This realization should not invoke terror. It should invoke a profound sense of humility. The calm authority we must cultivate comes from accepting that we are merely passengers. And as passengers, we must look beyond immediate geological symptoms and ask larger, more unsettling questions. Why are boundary condition instabilities manifesting now across entirely disconnected systems? While the physical link between Hawaii and Italy is non-existent, they reside within the exact same shifting planetary envelope. We must consider the invisible parameters that our models treat as static constants. The Earth's magnetic shield is currently undergoing a documented weakening phase. The geomagnetic poles are accelerating their drift. The upper atmosphere is experiencing anomalous sudden stratospheric warming events that displace the polar vortex, driving unprecedented atmospheric rivers across the continents. Could a rapidly shifting magnetosphere, or subtle variations in the Earth's core dynamics, be altering the background stress fields of the lithosphere? Are these volcanic anomalies the localized expressions of a much deeper, systemic planetary reconfiguration? Mainstream models are unequipped to process these macro correlations because they require crossing guarded academic disciplines. But the atmosphere, the magnetic field, and tectonic plates do not operate in silos. They are a single, violently interacting mechanism. This is the essence of investigative meteorology. We do not look at a broken Kīlauea cycle in a vacuum. We do not look at Campi-Flegre's hydrothermal pressure in isolation. We place them on the grand board of planetary behavior. While the mainstream attention economy remains anchored to the loudest disasters like the Japan Trench, we will continue to watch the quiet spaces. Because the truth is, the most dangerous events in human history never announced themselves with a global broadcast. They began as a quiet swarm of earthquakes in the wrong place. They began as an inch of uplift that no one could explain. They began with 3 words hidden in a technical bulletin. The cause is uncertain. The models have reached their edge. The map is blank, but the instruments are still running, and the Earth is speaking. Until the next data window closes, keep your eyes on the horizon. Keep your mind objective. And remember, in an era of compounding chaos, your greatest survival tool is your attention. In emergency management, cascading failure is the exact moment mathematical models stop predicting localized damage and start mapping systemic collapse. To truly embody the mindset of investigative meteorology, we must project our current data forward. We must run the simulation. Imagine the 7-2-hour window at Kīlauea does not stabilize. The south rim anomaly escalates into a massive lateral intrusion. A new fissure opens near critical highway infrastructure. The immediate hazard is lava, but the compounding hazard is airborne. Volcanic ash and sulfur dioxide saturate the atmosphere. Now, introduce a non-linear variable. The Pacific Ocean's record-breaking heat anomalies act as a massive thermal engine, generating a slow-moving, intensely saturated atmospheric river. When this atmospheric river collides with the dense volcanic ash plume over the Hawaiian Islands, the ash does not just blow away. It mixes to create highly conductive, acidic rain and catastrophic, heavy mud flows. This exposes the extreme fragility of our human overlay. Modern high-voltage power lines and substations cannot withstand conductive, acidic mud. Transformers blow. The grid drops. Instantly, A geological event becomes an infrastructure crisis. Communication towers rely on battery backups, lasting exactly 48 to 72 hours. Once drained, data stops flowing. The GPS arrays, tilt meters, and seismometers go completely dark. Science is blinded right when the system reaches maximum volatility. 4. Sitting thousands of miles away, you might think this is a localized Hawaiian or Italian problem. This is the illusion of distance. Our world operates on a fragile, just-in-time supply chain. If a compounding anomaly shuts down a Pacific maritime hub, or if Campi Flegrei paralyzes the Mediterranean airspace, shockwaves travel instantly through the global economy. Within 96 hours, cargo disruptions create severe shortages of pharmaceuticals and agricultural fertilizers. The fragility we discuss isn't just about power lines. It is humanity's absolute lack of redundancy in how we feed and sustain ourselves. We foolishly traded resilience for efficiency. Models predicting economic stability assume environmental stability. They assume ocean currents will behave, and the atmosphere will only deliver storms we have seen before. But the data shows the Earth is no longer playing by 20th century rules. You do not watch this channel for entertainment. You watch to gather intelligence and build localized redundancy. When institutional models issue official statements of uncertainty, that is your immediate cue to act. You cannot stop the South Rim from inflating, nor can you depressurize Naples. But you can secure your own off-grid power supply. You can build a robust buffer of nutrition, water filtration, and medical supplies. You can harden your personal infrastructure to withstand the shockwaves of a non-linear planet. The Earth is not plotting against us. It is simply operating at a scale and complexity our modern civilization forgot how to respect. Anticipate the cascade before it arrives. Build your physical resilience. And always remember, your most valuable asset in an era of unpredictable, compounding planetary shifts is a calm, prepared, and profoundly observant mind. We are entering a chapter where the Earth is moving faster than our models. In this era of compounding anomalies, outsourcing your situational awareness is no longer an option. Your greatest survival tool is your own attention. If you value this kind of objective, data-driven analysis, if you want to understand the reality of our changing planet without the noise of mainstream panic, then I invite you to subscribe to the channel. By subscribing, you are joining a global community of vigilant observers who choose to look at the hard science. Before you go, I want to hear your perspective. Drop a comment below and let me know. Between the sudden pattern break at Kīlauea and the persistent unrest at Campi Flegrei, which system do you believe represents the more critical blind spot for our scientific models right now? Let's discuss it in the comments. Stay objective, stay prepared, and never look away. I will see you in the next report.